So chapter 8 is on, last week we did solids, liquids, and gases. Now we're going to look at solutions. And early on I think we talked about solutions as a type of, actually another name for homogeneous mixture. Right? And all mixtures retain the identity of their components. So like salt water would have sodium chloride in it and water, and you can separate them by physical means. So that's what we're talking about with solutions. One other characteristic of solutions is their concentrations can vary within certain limits. Okay. All right, so these homogeneous mixtures, we normally think of solutions as a solid dissolved in a liquid, like sugar water or salt water, or we might stretch to a liquid in a liquid, like alcoholic beverages. They have ethanol and water and some other things. But solutions can come, homogeneous mixtures or solutions can come in any mixture of phases. Let's see, before I get too deep into this, who's coming in? David. Yeah, I think I do have something for you. Yep. Let me fix it over here. There you go. So we can have, well, everybody's familiar with a solution of carbon dioxide gas in water, usually with sugar added or non-caloric sweeteners. We call it pop. That's a gas in a liquid. That's a solution. A gas in a gas is a solution too. We breathe in that every day. Nitrogen and oxygen primarily. Solids and solids can be solutions also. Like brass is a mixture of nickel and copper. Now the difference is with solids, you can't just put the solids together and make a solution. You got to melt them first. Then when they solidify, you've got a solution. When we talk about, when we're defining the components of a solution, you've got a solvent and a solute. Yep. Another dead one. You can only have one solvent, one only, but you can have many solutes if necessary. Right? Maybe you only got one, but you can only have one solvent, and the solvent is always the major component. And what we mean by that, it has the highest concentration. Now there are solutions that start off with a major component, and then we add the minor component, and if you keep adding it, some of them are so soluble that you'll end up with more solute than you did solvent to begin with. But in those cases, we go back to the beginning. What are we putting into? What's holding the solute, and what are we putting it into? And that defines the major component. So example, sugar water. Right? We know we can mix 50-50 by volume of sugar and table sugar and water and make hummingbird feed. But you can just keep putting sugar in there and it'll go right into solution. It takes a lot of sugar to reach its saturation. But we still say that the water is the solvent and the sugar is the solute. Okay. We'll skip that. That's neither here nor there. Okay. So we've already identified the the first bullet point here. Solutions can contain two or more components, one solute and one solvent and as many solutes as you need. They can also have variable composition. So you can add more solute and increase the concentration of the solute. Consequently, you would decrease the concentration of the solvent, correct? I'll take that as a yes. Properties change. Solution properties change as you increase the solute. And there are a number of ways to identify those properties. The one that's most useful to us as chemists is they're called colligative properties. Like what happens to the freezing point of water when you add salt to it. Right? Well, you can make ice cream. Right? Freezing point of water will go down as you add salt to it. So we can make the freezing point of water so low that it will freeze mixtures of custard, right? Like frozen custard. That's just one of the properties that's possible to change with the concentration of the solute. In these homogeneous mixtures, the solutes are present as individual particles. They could be individual atoms. They could be molecules. The solution of air is diatomic nitrogen is the major component, and diatomic oxygen. And then you have some argon and some other stuff. But these are molecules, but they exist as individual particles in the solution. That's an atom. It's an individual atom in the solution, and they retain their identities. If we put sodium chloride in water, the sodium chloride as a solid is a crystal structure, remember, of sodium ions and chloride ions in regular arrangement. But when you put it in water, those ions break out of the crystal and they're surrounded by water molecules. So they're individual ions present in a solution of salt water. They will not settle. If you have a true solution, then it doesn't matter what you do to it, the solute will not settle out of solution. It's uniformly distributed, right? Homogeneous mixture, and it will not settle. A heterogeneous mixture that is made of, it's not a solution, the particles will settle over time under the influence of gravity, or if you put them in a centrifuge and give them some artificial gravity, they will settle out. There's one exception. I'm not sure if we're going to get to it, but I'll mention it now since it's stream of consciousness. You can mix a minor component with a major component and get what's called a colloid. A colloid is not a solution. In other words, there's one characteristic that the colloid shares with solutions. It will not settle out. But it doesn't settle out for a different reason. The individual particles in here, we say this the suspending medium and the suspended medium. Are analogous to solvent and solute. It's based upon particle size. The suspended medium particles are so small that the kinetic energy of the suspending medium keeps them from settling out. Does that make sense? It's a violent neighborhood. If you were down small enough to see it happening, you wouldn't want to get in its way. So how do you tell the difference? Right? Maybe you've never heard of this. How do you tell the difference between a true solution and a colloid? There's a very simple test. You just have your colloid in a container, a glass container, and your solution in a glass container, and you shine a light through it, a light beam of some kind. Right? So the light beam hits the colloid, and you're out here with your eyeball watching that one, and somebody over here is watching this one. And the light beam is strong enough so it'll go through both of them. When it tries to go through the colloid, you will see the beam reflected in the colloid because the particles are still there existing as individual particles that can reflect light. But when that light beam gets to this one, the solution, you don't see it. It goes through that solution without, you can't see it from the side. Okay? You can see it from over here, right? Because it's coming through there and hits your eye. But you can't see it from the side. That's the difference between the two. How to detect the difference between a colloid and a solution. And this is called the Tyndall effect. We use it in one of my general chemistry labs to find an end point of a titration. But that's neither here nor there for you. Okay. So I digressed. In either case, you can separate these components by physical means. In both cases, they retain their chemical identity. They don't change. Okay. So, in a homogeneous mixture containing 80 milliliters of water and 20 milliliters of alcohol, identify the solvent and the solute. Right? The major component is water, so that's the solvent. And alcohol is the minor component, that's the solute. Okay, I sort of alluded to this concept a little earlier, solubility. Depending on the nature of the solvent and its interaction with the solute. Now we're talking about solutions only. We're not talking about colloids anymore, just solutions. There is a limit to how much solute can be placed in solution before you reach a point where you can't put any more in it. There's one exception to that: gases. Gases are infinitely miscible, we say. They will form solutions with no solubility limits. All right? But for everything else, you have a limit of solubility. And for our purposes, we're going to try to limit our discussion to aqueous solutions where you dissolve solids in water. It's easier to understand if we restrict our discussion to that at this point. So, we're going to learn how to express that solubility in just a few minutes. But before we get there, how do we affect the solubility of a solute in a solvent? One way is with temperature. Most of the time, for most solutions, if you decrease the temperature, you decrease the solubility of the solute in that particular solvent. And if you increase the temperature, they become more soluble. There are exceptions in which increase in temperature will decrease solubility. But most of the time, you get an increase in solubility with an increase in temperature. Now the condition where this is solids in aqueous solution. As far as gases go in aqueous solution, right? We dissolve gases in, say, we carbonate water to make pop. Gases are the other way around. Gases are always less soluble as the temperature goes up. That has to do with the vapor pressure of the dissolved gas in water, and as you increase its kinetic energy, it has more energy to leave the solution. So, example. If you, I always hated to go to picnics where they had the 2-liter pop bottles sitting out in the hot sun. They had ice and they had cups, right? But they didn't refrigerate. They didn't cool the bottles of pop. So the first one that opened the pop across 6 picnic tables away, when they opened that, you could hear it. They go, psh, there goes all your carbonation because the temperature is too high. It decreases the solubility, so you get all that gas is sitting up there in the head just waiting to come out. So when you crack it, it's gone. It'll still fizz some, but not the way you want it to. I mean, that's the whole point of pop, is the carbonation. So, when I buy 2-liter bottles or any bottles of pop, first place they go when I get home from the store is in the refrigerator. And I don't open them until they've been in there for an hour or two. Till they're cold, all the gas is dissolved, is as soluble as it's going to get at that lower temperature. Then when you crack the top, you hear a tsh, that's it. And then you pour it on your ice, and it fizzes everywhere onto the floor. Okay. These are examples of solubilities of solids. And it looks to me that each one is more soluble as the temperature increases. Yes. We've got bromides, sulfates, chlorides, nitrates. More soluble as you increase the temperature. And that expression, that solubility of grams of solute per 100 grams of water, is a standard unit of measure that you will find in any reference manual. And they do it that way because you want to know if I have a certain amount of water, how much solute can I put in it? So that's why they express it that way. Grams of solute per 100 grams of water. That usually means 100 milliliters at room temperature. So you notice that there's a huge difference in the solubility at any given temperature among those different compounds, right? And that's typical. They vary all over the place. Come on. There we go. This is one example that they didn't put in the list. Calcium acetate. So how would we, what's the formula of calcium acetate? Let's see, there's calcium. And then acetate is C2H3O2, right? The acetate polyatomic ion has what charge? -1. How about calcium? What's its charge in an ionic compound like this? Look at the periodic table. Which group is it in? It's in the second one, right? So it has a 2+ charge. Right? So, to write the formula, we need 2 of those. That's calcium acetate. Then when you try to put it in solution, you want to cool the water down. It's more soluble. If the water is colder. Now there's no good theoretical explanation for that. You just have to, it's about trial and error. You know, which ones. Although it does appear that there are several of the acetates that exhibit that characteristic. In other words, that property, that decreased solubility with an increase in temperature. So, what good is that knowledge? Suppose we wanted to make a solution that it was saturated in a solute. And we know that it's more soluble as the temperature increases. And we're given the solubility of, say, silver sulfate. Okay, silver sulfate, and we want the solution to be in the neighborhood of 20 degrees when we use it. Right? So silver sulfate solubility would be between 0.5 and 1 at that temperature. So how would you make sure that the solution was saturated? You would heat it to 80, 90, 100 degrees, and then you would put into it about 1.2 or 1.3 grams per 100 milliliters of water, of that hot water. It go right into solution, and then you set it on the desk and let it cool. And as it cools, the excess, the insoluble solute that it can't hold anymore at a lower temperature will drop out of solution, and what's left is saturated. How about the effect of pressure? Would pressure have an effect on the solubility of a solid or even a liquid in water? No, because they're incompressible. You can't force them into solution more efficiently by increasing the pressure. But gases, yes, you can increase the solubility of a gas in a liquid, well, in aqueous solution, by increasing the pressure of that gas over the surface of the liquid. It's just by increasing the pressure, you are driving more of that solute into solution because more frequent and more forceful impacts on the surface of the liquid, that gives you more in solution. In fact, it's expressed quantitatively by Henry's law. So the concentration of your solute is proportional to the pressure on that solute. And then we need a proportionality constant, which varies with the solute and the solvent. So it has to be experimentally determined. But let's see. We talked about gases yet? Yes, we did. Okay. So remember the gas laws. If this is at one point, the concentration is that high for that pressure, then if we solve it for the constant, we say like that equals that constant. If we then increase the pressure, it's still equal to that solvent because we have a new concentration. So if you want to solve a problem, you just need to know before and after. Right? C1 over P1 equals C2 over P2, and that would give you an equation. If you know three of them, you can solve for the fourth one. Just like our P1V1 equals P2V2 for Boyle's law. Now they mentioned the H as Henry's constant. I've never seen a value for it. I always thought it was experimentally determined because gases behave differently with different liquids. So If there is a single constant that you can put in there for H, fine, but I don't know it. So if I don't know it, I'm not going to expect you to know it. You might find it in the book. I mean, if you find it in the textbook, then share it with the class. Okay. So I mentioned solubility in terms of how do you make a saturated solution. Saturated just means that there's as much solute in there as it will hold at a given temperature. And it is temperature dependent. For solids, and for gases, but gases are also dependent on pressure, so we've got another fly in the ointment there. Sometimes you can supersaturate a solution. That is, you can have more solute dissolved in the solution than you would expect at that temperature. And the best way to do it is with that technique I mentioned earlier. And when you set that hot solution down on your bench, cover it and don't touch it. Right? And use glassware that has no scratches on it. Then sometimes you can get it to supersaturate. In other words, it can cool down to room temperature and there's no precipitate in it. Nothing came out of solution. So we know at that point that it's supersaturated. It's gone beyond. The easiest way to get those crystals out and bring it back to saturation is to just go in there and maybe mix it, disturb it somehow, or scratch the inside of the glass, or drop a crystal of the solute in there. Give it something to grab onto, and it'll come right out of solution, and you'll end up with a saturated solution. Unsaturated simply means you haven't reached the limit yet. So that could be any concentration that's not saturated. Now when we discuss concentrations, we can do that in a semi-quantitative or a qualitative description, or we can use quantitative means and say exactly how much. In other words, numbers. But first, if we say a solution is concentrated, that means it has a large amount of solute and is in the neighborhood of saturation. It's a very high concentration. If it's dilute, then it's a very low concentration. And then you have in between. Sometimes you can tell if the solute acquires a color when you put it into solution, and some of your examples here for your lab are just like that. The cobalt solution is, I think it's blue. Cobalt solid crystals, the cobalt chloride solid crystals are going to be red. When you put them in a solution, they turn blue. So with that color, as you increase the concentration, say you have the same amount of the solute, but you have less volume of the solvent, then the color is going to become more intense. There's no chemical change there. It's just a matter of concentration. And you can see the difference here in that example. With the same amount of the solute in both beakers, but less volume in the one on the left, you see that its color is more intense. It's a deeper, darker blue, and you can't see through it as well. We've been talking for the past several slides about aqueous solutions. And whenever you say something is in solution, like say silver nitrate in aqueous solution, right? We follow it with AQ. I think we mentioned already, if you have a solid, we put an S, a liquid an L, and a gas a G. This is the other suffix to the chemical name or the formula. Non-aqueous solutions, I suppose you could specify what it's dissolved in. right? Inside the parentheses, you might say ethanol, if that's the solvent. But there's no standard for that. How does the temperature and pressure affect the solubility of gas in water? Increase the temperature, gas solubility goes down. Increase the pressure, solubility goes up. Now, you know, did I mention this last week? I can't remember which class I was in. When you put water on the stove to boil, when it starts getting hot, what does it do? What do you see? Huh?
Vapor, like gas.
Okay.
Steam,
All right, before you see the steam, what do you see?
bubbles
And where do they form?
in the pot.
They form on the walls of the pot. That's where the heat is. What you see first is not steam. It's dissolved gas coming out of solution as we increase the temperature. Right? Increase the temperature, gas is less soluble. So any air, any nitrogen, any oxygen, whatever else, dissolved in that water is going to come out of solution. And most faucets have kind of built-in devices that aerate the water anyway. Unless you do like me and you take them out, because they restrict the flow. I especially do that in my shower. I don't want flow restrictors in my shower. I want to get hit hard by the water. In the morning, that's what wakes me up. So now we're going to try to shrink ourselves down to the size of our solvent and solute and see what's happening at the molecular level. This is how a solution forms. Okay, so if we have the solute over here and the solvent over here, and we have the solution over here, down here. When we put them together, we get our solution. Okay, so we've got molecules of the solute attracting one another. Right, they're holding together. Say they're solid or a liquid. Right, the strength of attraction is going to be greater for the solid than it is for the liquid. And our solvent over here, let's say it's a liquid, right? It's got attractions of its own to hold the molecules in that phase. Well, in order to get these molecules to enter any kind of interaction with these molecules, you got to get them apart from each other. So we have to put energy in here. This is an endothermic process. Endothermic. We need to break bonds. And we're not talking about the bonds that are holding molecules together. We're talking about that are holding the molecule internally together. We're talking about forces that are attracting one molecule to the other. The intermolecular forces. So let me qualify that. Break intermolecular bonds. There we go. Got to break those apart. And the solvent has to do the same thing. So that's an endothermic process because we have to add energy. So we also have to break here intermolecular bonds. Okay? Sometimes we call it make a hole. Someplace for the solute molecules to go. Get these apart so we can put those in there. Now, when they come back together, they form intermolecular attractions to one another. Those are more stable. They give up energy. So this is an exothermic process. And we form new intermolecular bonds. Okay? So, what does this mean in terms of, say, the temperature? The endothermic process here is going to draw heat from its surroundings. All right, so we would add energy, and here we get some energy back. Okay, so this total is an input, and this is interest on our money. We're getting something back from here. The balance between the two, let's call this, we generally use a small Q for heat. So let's say we put heat in here, and this is the heat for the solute, and this is the heat that we put in for the solvent, and this is the heat we get back for the solution. Okay? And then we can add those all together. So we could say total heat is the sum of these. So Q solute plus Q solvent plus Q solution would give us a total value. Now, if we put more energy in here than we get back here, the overall process would be what? If this is greater than what we get back, the entire process is endothermic, right? But if we put some energy in here and here, and we get a whole lot back here, more than we put in, then the whole process is exothermic. Okay, we get energy back. And if you work in a hospital or you've ever used hot packs and cold packs in the hospital, one is designed, the hot pack is designed so that more energy comes back from the solution than you put in. That makes it hot. With a cold pack, you put a lot of energy in and you don't get much back. So then the pack gets cold. All right. All right, so that's the molecular explanation for solution formation, how we form a solution. Now we want to say a couple of words about how fast solutions form. The rate of solution formation. What would make a solution, how could you make a solution quicker? What can you do to make the solution faster than, under what circumstances? One of the ways is to decrease the particle size of your solute. If we're putting a solid into a liquid and the particle size is smaller, what does that do to the surface area? It goes way up. You increase the surface area of contact with the solvent, you'll make it go into solution much faster. Okay? The other way, okay, so let's see, rate of solution formation. One is solute particle size. And this is dependent upon, the reason it happens is surface area. Surface area in contact with the solvent. Okay? Second is agitation. If you just put, if you drop salt in some water and let it sit, eventually it'll go into solution. But it'll take a while. But if you stir it up, it's going to happen faster. The reason is that with agitation, you bring those particles into fresh solvent contact. Because each one of those particles of your solute is surrounded by the solvent, and as part of the solute goes into solution, it increases, it has a zone around the particle that's higher in concentration than the rest of the solution. It's not equilibrated yet. So what that means is the movement of the solid into solution is slowed because it sees all of its neighbors out there in the way. But if you agitate it, then you move them away from the particle and introduce fresh solvent, and that dissolves it faster. Okay? Third, we've already mentioned, temperature. For most solids, increase the temperature. Now, this argument is not going to work too well for those that are more soluble as the temperature decreases. But for those where the temperature increases solubility, you can make them go into solution faster, and it's purely due to the kinetic energy of the solvent. Those solvent molecules are moving faster and faster with more kinetic energy. When they slam into the surface of the solute, they knock pieces off of it at the molecular level. That's why we don't have a good explanation for why some things are more soluble with colder temperatures, because this kinetic theory doesn't work for them. Common ion effect. This one might be the most difficult one to grasp. Not saying you won't. It's just my experience is this one is harder to grasp. Let me put it this way. If your solute is only slightly soluble, then if the solvent already contains some of the ions that would be present from dissolution of your solute, they interfere with movement of the solute further into solution. They decrease, it's called a concentration gradient. And that also works with agitation. If you increase the concentration around the particle, then you decrease its movement into solution. And if there are ions that are common to your solute already in solution, they will decrease the rate of dissolution of your solute, because it's like they're competing for space. Okay. So, general rules for solubility. How can we qualitatively understand solubility? I'll give you the rule of thumb. You may have already heard this one. Like dissolves like. What we mean by like is polar versus nonpolar. In other words, if the solvent and the solute are both polar, they're more likely to form a solution. And the greater the polarity, the higher the solubility. But if you try to put a polar solute into a nonpolar solvent, you're not going to get a solution. For instance, you try, water is polar. We talked about that before, I'm pretty sure. Water is a polar molecule. If you try to dissolve it in oil, what are you going to get? Nothing. You're going to get 2 layers. It's like trying to make salad dressing, right? Vinegar and oil. The only way to make that work for your salad is to put them in a container and just shake them till you get dizzy. It breaks up the particles in little small pieces, and then you may throw some Mrs. Dash in there if you're making your own, season it. And then you pour it on your salad before it has a chance to separate. Those are insoluble because one is polar and the other is nonpolar. Okay. Let's see. This particular table is meant to describe soluble versus insoluble in aqueous solutions for different compounds of cations and anions. But since this is not a general chemistry course and you guys are not going on to get chemistry degrees, I'm not going to make you memorize these. There are rules that you go by that determine solubility. So what I've done is brought in, and these are the rules here. We can come back to them if you want. What I've done is given you this chart, and I think it's in, let's see, in the handout I gave you, review problems. If you look on the back of it, you'll see that chart. Okay? And as always, if the review document has information in it like that, useful information, it will be on the exam. Okay? So you'll have this chart to go by on the exam to determine solubility. The way you use it is the cations are across the top, anions are down the left-hand side. You just find out where they meet. Cation with an anion, and if the block is clear, then it's soluble in water. If it's grayed out, it's insoluble in water. Okay? So for example, if we take sodium and go down, take your pick. Anything that's combined with sodium is soluble in water. Potassium the same way. Magnesium is a little pickier. Magnesium nitrate, chlorate, hypochlorite, magnesium chlorite, magnesium chlorate, magnesium acetate, chloride, bromide, iodide, sulfate. Those are all soluble. When you get down to hydroxyl, magnesium hydroxide is insoluble. So that's how you read that chart. There are some exceptions in there, and they're identified down below. Okay, so those are your solubility rules. And if we have a chemical reaction between two compounds that are in different solutions, put the solutions together, and then the ions have a chance to mix, then you can see cations from one with anions of the other. What happens, right? And you look them up, say, are they soluble? Okay, we just put an AQ next to them as a product. If you put the other cation and anion together, it's a double replacement reaction, and look it up and it's got a gray box, then you put an S next to it because it is insoluble. It turns into a solid and gives us what's called a precipitate. It just drops out of solution. All right, let's see. Do I need to go back? Did I skip something? Just the rules. That's okay. You can look at those rules. If you ever want to use these rules, they're set up in order 1 through 7, so that if you find yourself with a cation anion together and it fits 2 of these categories, the one that takes precedence is the smaller number. Right, so look at group 1 elements. Lithium, sodium, potassium, rubidium, cesium, and francium, and ammonium compounds are all soluble, always and forever. Second one, nitrates, chlorates, perchlorates, and acetates, they're all soluble. So any metal ion combined with those anions is soluble in water. And then you have further down the line. So if you come down here, you find one that conflicts with the one above wins. Okay. So let's go back over here. The greater the difference in the solute-solvent polarity results in less solubility of the solute. You can get polarity is on a gradient. So you can get extremely polar compounds, or you can get slightly polar compounds. Example, water, like this, like that, is polar in that direction. So it's negative on this end and positive on this end. Ethanol, drinking alcohol, is CH3, CH2, let's see, let's do it this way. C, H, H2O, H. This part of the molecule is very polar, just like this part of the water molecule. Right? But it's got these non-polar out here, so that moderates the polarity. So this one is less polar than water. So something that's soluble, completely soluble in water, won't be as soluble in ethanol, usually, because of that difference in polarity. So here's an example. Let's take any one of these anions, and E is in there as a ringer. Right? Are you going to form a compound with lead and sodium? No, not the ions. Right? Now, if you have sodium metal and lead metal, it'd be difficult to make an alloy out of those because sodium is so reactive. So sodium is just thrown in there to see if you are paying attention. You're not going to form a compound with lead and sodium. So we're looking at the other anions. And we say, which one of these is generally soluble? Right? So if you take lead and you go back to your chart, let's see, let me put those up here. So I can go back to our chart. Let's see, sulfur, chloride, nitrate, and sulfate, right? And we're going to form a compound, each one of these with lead. Lead 2+. Okay. 2 minus 2 plus, 1 to 1, that's fine. Here we got a negative 1, so we need 2 chlorides. We also need 2 nitrates for this one to balance the charge, and these are 2 plus, 2 minus, so they're good. Those are the possible compounds. Now, which of these would be soluble? Now, if you know the rules, you know that all nitrates are soluble. That's definitely soluble. But if we go back to the chart, right here, we find lead, and it's the second one from the right on top. We follow it down, we find nitrate is soluble. Okay. Acetate. We don't have those others. When we get down to chloride and below, those are all insoluble. Okay? So the only one that's soluble out of that group is the nitrate. All right. Here we go. Nitrate. Now, how do we express concentration for a solution? I mentioned earlier that one of the characteristics of homogeneous mixtures or solutions is that they have variable composition. The concentrations can change. Well, there are several ways we can do it. Two of the most common are percent composition, and it depends on the units of measure. If we do percent, remember percent is a dimensionless number. You can't tell by saying percent whether it's mass of the solute per volume of the mixture or the solvent, or is it mass of the solute per mass of the solvent or mass of the solution, or volume, right? This is alcohol, right? If you go and pick up a bottle, it's going to say a bottle of wine, 15% ABV, alcohol by volume. So that means the alcohol is expressed as volume and the total is expressed as volume also. What's the standard concentration of beer? Anybody know? 6.4% ABV. Now there was a time when federal law restricted the concentration of beer to 3.2%. But that was repealed. Okay, so percent composition can be in terms of mass volume, mass mass, or volume volume. And you have to specify, or you have to deduce from the problem what those terms, what those values are. Because percent just means parts per 100. You don't know what the parts are unless you're told. The other possibility is called molarity. Right, I've got a slide on that, so I better probably just, I think I should. I got a slide on it. Yeah. Okay, so percent, the Achilles heel of percent is that it's dimensionless. Percent by mass, percent by volume, or a combination. Actually, you could do volume per mass also. But usually if you've got mass and volume together, the solute is expressed as mass and the solution is volume. Percent by mass is fairly common. And when we use mass to express concentration, it's equal to the mass of the solute divided by the mass of the solution times 100. Okay? So the mass of the solution is going to be the mass of the solute plus the mass of the solvent. The nice thing about this is it's not affected by temperature. Right? You don't change the mass with temperature. Whereas if we have volume introduced, then you got to take temperature into account because volume will change with temperature. So mass percent, mass percent is a convenient way to express concentration. Okay, how about this one? Percent by mass if you have 5.5 grams of glucose and 78.2 grams of water. What was that, 5.5? Yeah. So our solute is 5.5 grams. What's the mass of the solute the solution. 5.5 plus 78.2 grams, right? And they have to be the same units of measure for grams, for mass, but it doesn't matter what it is. As long as they're exactly the same units, then this works. Times 100. And I think it's, there it is, 6.6%. Percent, mass, mass. Okay, percent by volume. If you do volume of solute and volume of, I'm not so sure about this, volume of solvent. You can express it that way, but more often than not, it's volume of the solution rather than the volume of the solvent. So that has to be specified also. If you have, say, mass of the solute and mass of the solution, your percent value will always be equal to or less than 100. But if you express mass of solute per mass of solvent, you can exceed 100%. Okay? Because if it's extremely soluble, like table sugar in water, you can put more solute in there than you have solvent. And the fraction then becomes greater than 1 times 100 is 100, greater than 100%. Okay. So, what's the volume percent of solute in 30 milliliters of methyl alcohol in enough water to give 435 milliliters of solution? See, that's why I think that they they made a mistake on that previous slide because of the way they want you to calculate in this subsequent problem. It should be volume of solution. Let's see. Didn't tell us. 30 divided by 435. Oh, there it is. So if you have 30, wait a minute. There's another mistake. This one says 30 milliliters of methyl alcohol in 435 milliliters of solution. And then the subsequent slide, it's 30 milliliters of ethyl alcohol in 435 milliliters. Which one should you not drink? The first one. Methyl alcohol is wood alcohol. That's the one that makes you go blind. Now, it's produced at the same time during fermentation as ethyl alcohol in smaller amounts. So, if you're a moonshiner and you don't want to blind your customers or kill any of them, as you're distilling the mash, the first fraction that comes off is going to be the lower boiling point, the methanol. So, you boil that off and you catch it and throw it away. And then you keep the rest of it in your mason jars, I guess is standard practice then. I don't know. I've never bought White Lightning before. I had my professor, one of my professors he did field work in North Carolina, South Carolina, Virginia, for the Phosphate Potash Institute. And they'd go out and visit with farmers and various people. And one time they helped this customer with a problem, and as gratitude, as they were driving away, look in the back floorboard and there were 6 mason jars of White Lightning. And my boss leaned over to the guy he was working with, who was his boss, and he says, did you see that back there? He says, oh yeah, he's just being friendly. He says, we'll go down the road a ways and dump it. Okay, so if you divide 30 by 435 times 100, you get 6.9%. alcohol by volume. So the previous slide needs to be changed. That's a serious error. Mass volume percent. Usually, mass volume percent here is expressed as grams per 100 milliliters of solution. That way, if you divide grams by milliliters times 100, that is per 100 milliliters of solution. Okay. Now, once you've determined the concentration of a solution, it can be used as a conversion factor. We see a ratio here, say 6.6%. 6.6 grams of solute per 100 grams of solution can be used as a conversion factor. Let's take that as an example. Grams of, well, let's put something in here. Say sodium chloride per 100 grams of solution. Okay. If we have, say, 25 grams of solution, can we find out how many grams of sodium chloride are in that sample? Yeah. So grams of solution on the bottom, right, to cancel this on the numerator, and then grams of sodium chloride on top. So we have 100 grams here, and we have 6.6 grams here. There's our conversion factor, and we can determine how many grams that we possess with that much solution. Okay. It's a conversion factor. Okay. Mass percent concentration of 10% means that we have 10 grams of solute per 100 grams of solution, or 90 grams of solvent, because the total has to be 100, doesn't it? Yep. So there's your answer. 10 grams of solute and 90 grams of solvent will give you 10% mass. Okay. I should have waited, because there's a conversion factor problem right there. How are we doing on time? Okay, we're good so far. So for this problem, how many grams of sodium chloride are needed to prepare 150 milliliters of 0.9% sodium chloride? 0.9% will be our conversion factor. If we need 150 milliliters of solution, we need a conversion factor that will give us grams of sodium chloride for that solution. All right, 0.9%. What does that mean? Mass volume. Well, the volume in milliliters and the mass on top. So that's 0.9 grams of sodium chloride per 100 milliliters of solution. So there we get our cancellation, and we're left with grams. Let's see, that's 1.35 grams of sodium chloride. Now, why would we need to know that? If you're going to make a 0.9% mass volume sodium chloride solution, and you know the volume, the final volume, then you need to put that much mass of sodium chloride in that many milliliters of solution. Right? So in that case, you need to have the ability to measure exactly 150 milliliters of solution. You need a container of some kind that's calibrated for 150 milliliters. Because if you say 150 milliliters of water and you put sodium chloride in it, it might be more, it might be less. Right? So you need a way to determine the exact volume of your solution once the sodium chloride has gone into solution. That's where volumetric glassware comes out. I don't know of any that are 150 milliliters. They're usually, I've seen as small as 1 milliliters volumetric flask up to 5 liters, a huge one. But I've never seen 150 in that mix. They usually go 50, 25, 50, 100, 200 and 250s, 500s, 1 liters. It's usually how it goes. Okay, that's mass, and mass volume. Now for chemical reactions, molarity works better. Can you imagine why? The key is in the moles term. Remember, you can't go anywhere in a balanced equation unless you have moles. And if your reaction is with solutions, then you need to know their concentration and the volume that you put together in order to determine the moles of the reactants. Otherwise, you're stuck. So, molarity. Molarity is given a capital M to represent molarity. And one of the reasons that we use a capital M is because there's nothing on the periodic table, it's just a single M. So you can't get it confused with any of the elements. This is molarity. And it's defined as moles per unit volume. That's my little n with no zero on it. If there's a zero on it, what is it? It's a neutron, right? But there's nothing up here, so that means moles. This is moles, and the unit of volume has to be liters. This is liters of the solution. This is moles of the solute. Okay? That's the definition of molarity. So if I were to put 1 mole of sugar, table sugar I assume, in 125 milliliters of solution, what's the concentration? You have to be sure you use the right units of measure. We got moles already, right? 1 mole of sugar. Let's see, it's got 2 zeros. And what's the final volume? 125 milliliters. Now I have seen volumetric flasks at 125. But that's not liters, right? How would you convert 125 to liters? 125 milliliters to liters. Well, if you do this enough, you know that you just move the decimal 3 places to the left. 1, 2, 3, 0.125 liters. The other way to do it is to say, what does milli mean? Milli means 10 to the minus 3, 1,000th of, right? So we substitute 10 to the minus 3. Instead of milli, we put 10 to the minus 3 times this one. And then if we convert it, right, to scientific notation, right, we take 2 of those negatives and move them over here, 1.25 times 10 to the minus 1 liter. And we know 10 to the minus 1 is a tenth of that, so it'd be 0.125 liters. Okay? So that's the long way to do it. Short way is just to know, move the decimal 3 to the left, and you got liters. Right? So 0.125 divided into 1 gives us 8 molar. Sucrose solution, aqueous solution. Okay? That's molarity. Now the advantage to that is we know that if we possess 1 liter of that solution, we also possess 8 moles of sucrose. How about if we have a half a liter? Then we only have 4 moles, right? Say we have a tenth of a liter, or 100 milliliters. We only have 0.8 moles. Okay? That's the beauty of molarity. It's very easy to calculate what you have with a given volume. Oh, by the way, with this formula, it's like any mathematical expression, right? You've got 3 variables there. If you know 2 of them, you can solve for the third one. So if we need moles, if we know the molarity of our solution times its volume, we can calculate the number of moles. Okay, if you have 10 molar sugar solution, what volume of this solution do you need to have 2 moles of sugar? Right? So in this case, we'd solve it differently. We're solving for what? Volume. So solving for volume is that. Right? So we want 2 moles out of a solution that is 10 molar. Right? And if you need to visualize the cancellation of units, just say, what does molar mean? It means moles per liter, right? So moles cancel, liters in the denominator, which makes it in the numerator. So our volume is going to be in liters. And 2 divided by 10 is what? 1/5 or 0.2, right? So volume is equal to 0.200 liters, or 200 milliliters. Because now we're going bigger to smaller means smaller to bigger. So 1, 2, 3. 200 milliliters. It's probably going to be in liters though. I got this one animated. There you go. 0.2 liters. That's the volume you need of that solution to give you 2 moles of sugar. All right. Okay, we'll get most of it off and then I'll clean up the ghosts. There we go. Oops. All right, consider separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each in 250 milliliters of solution. What's the concentration of each solution? Well, since we're in molarity, I assume they're asking for a molar concentration. So we've got 100 grams of each. 100 grams of sodium hydroxide and 100 grams of potassium chloride. Okay? If we're going to calculate molarity, we have to know the moles, don't we? So that means, what do we need for our conversion factor? We want to get rid of grams. These are with moles. When you see grams and moles in a quotient relationship, always think molar mass. So what's the molar mass of sodium hydroxide? Sodium's 23, I believe, rounded off 2 places. So that'd be 23. Oxygen 16. And hydrogen's 1.01. And so that's 40.01 grams per mole. Moles are on the top though, so grams goes down here. Okay, that'll give us moles of sodium hydroxide. How about potassium chloride? Potassium's what, 39? Yeah, 39.10 rounded to 2 places. Let's see, let's put it out of the way. And then chlorine is 35.45. 74.55. So this one converted would be 74.55 grams per mole. That'll give us the number of moles of potassium chloride. Okay? That's just the first step. This is 2.499 moles of sodium hydroxide. And this 74.55 is 1.341 moles of potassium chloride. Now we can divide them by our volume. Once we convert it to liters, how many liters is 250 milliliters? No idea? We just did one. I mean, it was 100 milliliters, but do the same thing with these milliliters. No idea? Brains are shot, right? They're fried. That many moles, 0.250 liters. Okay? So now, let's see. I'm going to do this one first since it's in here. 0.25. This is 5.3, 3 significant figures. I'm going to round it off to 5.37 molar potassium chloride. And this one is about 10.0 molar. Okay? So, okay. There's the first one, there's the second one. The moral of this story is you got the same mass of each compound, but you got different moles. So when you put them each in their own same volume, you get different molarities. The only way we could get the same molarities out of 2 compounds is if they have exactly the same molar mass. And some of them do. But you have to calculate to be sure. All right. Let's see. Yep. Okay, we're good. Dilution. So you've got you've prepared a solution of a given molar concentration, molarity, but it's too concentrated. And you don't want to have to go back and make a new solution with the same materials, only with more solvent so that you can reduce the concentration. What do? You dilute it, but you dilute it quantitatively. You know by the procedure that you're going to end up with the concentration you want, starting with the higher concentration. Okay, so here's what it looks like in a practical way. You've got this concentrated solution here. Right? This is molarity of the concentrated one. And you want to end up, since we're going to dilute it to a known volume, we need a volumetric flask, something that is calibrated to hold a certain volume. So I'm going to draw the volumetric flask as a long neck on it, and then a big bulb at the bottom, and it has a mark up here somewhere. And that tells you that when you fill this up with your solution to that mark, you have exactly the volume indicated on the glassware. So let's make it simple. Let's say, well, no, we're going to be generic about this. The volume here is the volume of the diluted solution. Okay? And we want a concentration that's less than the concentrated one. Okay? So, in order to make this solution, we need to put a certain number of moles of the solute in here and dilute it to that volume. And when we do, since M equals moles divided by volume, and moles equals M times V, then M times V equals the number of moles that we need in that vessel. Okay? So how do we get those moles over there? We bring them from here. Okay? We get the moles coming from there over here. So if we need this many moles here, what happens as we go from here to here? Nothing. The moles we draw out are the same moles we put in. Right? So the moles from the concentrated side are equal to the moles of the product side. Okay? So we know that this is true. Those are equal. And we know that this one equals that expression. Molarity times volume. How do we get that one? That number of moles is also equal to this molarity times the volume that we extract from here. Okay? So that's where that expression comes from. In this case, well, we got it written two ways. Stock versus diluted, right? Concentration of stock times the volume of the stock yields the concentration of the diluted times the volume of the diluted. Or M1V1 equals M2V2. We used to do this in our soil testing lab. Well, soil testing lab was across the hall, but I was soil testing too, so I would make up concentrated solutions of a particular concoction that I was going to use to put in the soil and extract elements from it. But some of the compounds that go into solution take a while to dissolve. Right? So I said, all right, I'll just make up a concentrated solution, and then it'll be ready. They'll all be in solution. Then all I have to do is dilute them to the working solution, and that'll happen quickly. Because they're already in solution, I'll just dilute them now. And this is the expression that we used to determine how to dilute our stock solution to a working solution and then go do our extractions. That's when the fun starts. Once you get the extractions, then you have to filter them and collect that solution, and then you have to run it through your whatever to find out what's in it. I think at that time I was using atomic absorption spectrophotometry. Okay. How would you prepare 100 milliliters of 0.9% saline solution in water from a 10% saline solution? All right. So here's what I do. Just to keep things straight, I set up my chart. If I recognize it as a dilution problem, which this obviously is, then the diluted solution needs to be 0.9% salt. And in this case, we're not molarity. Right? So to be proper, I should just use concentration. Right? Because that's not molarity. So concentration of the diluted one is 0.9%. We're working from what? 10% saline. So this one is 10% saline. We want to know how to prepare 100 milliliters. That's the final volume of this one. So when you do it that way, then you're sure to get things in the right place. Then you can bring them to your formula and not put them in the wrong place and get the wrong answer. All right, so we want to know what volume of the concentrated we need to pull out to make 100 milliliters. So I'm going to erase this to make room. And if our expression is concentration of the concentrated one times the volume of the concentrated, and the concentration of the diluted one times the volume of the diluted, then we solve for our unknown, which is this one. There we go. Now all we have to do is plug the numbers in. Okay, I think I finally used up all these and they go in the trash. Let me get one that works now. So we put the values in here. This is our unknown, so we're going to put concentration of dilute 0.9%, and the volume of the dilute is 100 milliliters, and the concentrated is 10%. Okay, notice that the percents cancel, and we're going to be left with milliliters as our answer. That's because these are all ratios. So as long as we're using the same units of measure, we don't have to worry about, converting to whatever. They're going to come out in milliliters. So 10 into 100 is 10, right? And 10 times 0.9 is 9. 9 milliliters of the concentrated solution, or 10%, dissolved in 100 milliliters. Okay, I got this one animated. I forgot about that. Okay, so what we're saying is, and this is not this is going to be very rough, but it should work as long as the density of the concentrated is roughly the same as the density of the dilute. 9 milliliters of stock plus 91 milliliters of water, and we're assuming we're assuming that the solution comes out 100 milliliters, but it doesn't necessarily have to. Well, it's more likely if you put a solid in solution that you're going to get a wide discrepancy in the final volume. But when you've already got it diluted, then it usually comes out pretty close. But what you would really want to do is take 9 milliliters of the concentrated solution and put it in a volumetric flask that's 100 milliliters and dilute it to volume. That would guarantee that your solution was 100 milliliters. Oh, okay. I forgot I annotated that one. Okay. So, a 0.5 molar solution of sodium chloride sits on a lab bench. Which of the following would decrease the concentration of salt? Decrease the concentration. The salt is not volatile. So whatever you have in that 0.5 molar solution is going to stay there. The only thing that's going to evaporate potentially is the solvent, water. So if we let the water evaporate, we're going to increase the concentration. So add water to the solution, yes, that would decrease the concentration. It would dilute it. So A is definitely an answer. Pour some of the solution down the sink. You're pouring water and salt at the same time and at the same rate. So that wouldn't change the concentration one little bit. Add more sodium chloride would increase the concentration. Let the solution sit out and evaporate, that would increase the concentration. And the last one is just stupid. Okay. All right. Let's clear the board. Okay, what's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide? All right, what we need here is to set up our table and put the values in it. So in this case, we do have molarity of the concentrated and volume of concentrated, molarity of the dilute, volume of the dilute. So 2 molar sodium hydroxide is the concentrated, and the dilute is 0.8 molar. Okay, so what is the minimum volume of this one to make 150 milliliters of the diluted one? And notice, since these are ratios, you don't have to change that to liters. It's only when you're calculating concentrations with the standalone formula, molarity equals moles divided by volume, that's when you have to make liters. But when you've got a ratio going, then you don't need to. Right? This concentration is going to come out in those units because these cancel. So I think I have it animated. Let me see. No, I don't have it animated. So you would just solve for the if this one equals this one, then you would solve for the unknown. And put in your values. So this would be 0.8. This would be 150. Right? Dilute, 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 and concentrated is 2. And that should give you, let's see, it'd be 0.4 times 150. Or 4 times 15. 4 times 15 would be 60, right? 60 milliliters. I like to do things in my head as often as possible. It keeps my synapses working. Calculators are nice. But if you find yourself without a calculator, what do? You got to know how to do it the old-fashioned way. Okay. All right. So I mentioned this one earlier. This one shouldn't take too long because I've described it all the way up to this point. This is a colloid or colloidal dispersion. It represents a homogeneous mixture, but it's not a solution. It contains dispersed particles that are analogous to the solute and a dispersing medium that is analogous to the solvent. And it's based upon the fact that the dispersed phase is the particles are suspended and will not settle is based upon size. And there's the Tyndall effect, right? Shine that light beam through both of them, and the one where you can see the beam go through the solution is a colloid. Now, when you think of colloids, think Jello. Jello is a colloid. There's an example. So the solution is on the left. You can't see the beam. But when it reaches the colloid on the right, you can see the beam going through that. If they were both solutions, you wouldn't see the beam going through them. All right, so suspension is a heterogeneous mixture that contains dispersed particles that are heavy enough they will settle out under the influence of gravity or in a centrifuge. They will eventually settle out under the influence of gravity, but they may take a long time. So if they're too big to be dispersed as a colloid, but not big enough to settle out in your lifetime, then you put them in a centrifuge and you increase the force of gravity by thousands of times, and that makes them settle faster. Okay, let's see. I'm going to let you look at this one on your own. This just summarizes everything we've talked about up to this point, and it's straight out of your textbook. Colloidal dispersion is all of these. It contains small particles that are not visible to the naked eye. It's a mixture that contains those particles that do not settle under the influence of gravity. And it contains particles that cannot be filtered through large pore filter paper. Now, if you have filter paper that has small enough pores, then you will be able to remove the suspended medium. But it takes very, very small pores. In other words, the ones I've seen are made out of Teflon, and they look like a solid sheet, but they've got microscopic pores in them. And when you put your solution in it, it's just going to, not solution, you put your colloid in there, it's not going to filter. What you have to do is pull a vacuum. Pull a vacuum in the vessel below it. If that doesn't work, put a cap on the top and put pressure on it. You've got to force them through that filter in order to remove the suspended medium. Okay. Are you familiar with the concept of homogenization? Milk that we buy in the grocery store is both pasteurized, right? It goes through a heating process to kill the bacteria so it'll last longer. And it's homogenized so that the cream will not rise to the top. The fat is suspended. That's a colloid. How do they get those fat particles so small? Used to be, you'd use a bladed mixer and it would just chop them up. But on the industrial scale, you need to work faster than that. So what they do is they take milk and they run it through a stainless steel sieve that has very, very small holes in it. And they put it under very high pressure. And it drives it through there. And the only way the fat can get through there is to break into small particles to go through those holes. So that's how they break up the fat into small particles that stay suspended. They drive it through those filters under very high pressure. Okay, what are colligative properties? First of all, colligative properties of any solution are physical. We're not talking chemistry at all. And they depend, the colligative properties of the solution depend on the number of solute particles. And we can express those in terms of concentration. It doesn't depend on the identity of those particles at all, only on the numbers. So that's one convenient way of these colligative properties can be used to help us determine. Somebody talking? Okay. They can help us determine the molar mass of an unknown compound, because we can put a certain mass of a compound into a solution, test the colligative property, which tells us how many particles are there, and that is interpreted as moles. We have mass and moles. We can determine the molar mass of that compound. I think we're going to do one. Yes, molar mass by freezing point depression. That's we're going to do Boyle's law next week, and then the following week we're going to do colligative property, freezing point depression. Other colligative properties, freezing point depression and elevation of boiling point. Boiling point elevation is another one. Lowering vapor pressure. If you add a certain amount of a solute to a solvent, it will lower the vapor pressure of that solvent. And osmotic pressure. We have to define what those terms are. I think that's coming up. So, vapor pressure, we have to define, did we define what vapor pressure was? Yeah, last week we did, didn't we? Yeah. So, if we have a vessel, or a flask, say, and we stopper it, we have a liquid here, then it's going to start sending these, this is pure, right? This is a pure solvent. It starts sending molecules into that headspace. And at first, it's a one-way trip. They're all going that way. They're evaporating. But once we build up some pressure here, and we get so many of them in the headspace, then they start coming back. Right? And we get an equilibrium set up to where the evaporation is equal to the condensation. Okay? And that develops is unique for each material, each liquid. It gives us a unique vapor pressure. Right? And that's for the pure solvent. That was not doing too well either. Let's see. Bring out a fresh one. Okay, so what happens if we, let me draw it bigger this time. What happens if instead of the pure solvent, we have the solvent and we have solute molecules in there? Right? Well, at the surface of the liquid, two things are happening. One is these solute molecules are occupying space at the surface of the liquid. So the solvent doesn't have the opportunity to evaporate because that space is taken up by a solute molecule. Right? So that's one way that we decrease the vapor pressure here. So this is the pressure of vapor pressure of the solution. The other thing is intermolecular attractions. So if these solutes are actually in solution, you know they're attracted to the solvent. So what they're doing is they're attracting the solvent and it can't get away into the headspace. So the pressure is decreased. Okay? All right. There's a unit of measure that allows us to ratio the solute to the solvent. It's called the mole fraction. So if we have the total number of moles of both solvent and solute, and we also have the moles of the solute, that fraction is the mole fraction of the solute. Right? And it's got to be less than 1. Oops. It has to be less than 1. So what would be the mole fraction then of the solvent? Well, we could calculate it by this. Solvent moles divided by the total. But this one plus this one must equal 1 because it's a fraction. If we account for everything that's in that vessel, then this fraction plus that fraction has to be equal to 1. So if we calculate the solute mole fraction, then the solvent mole fraction is 1 minus the solute fraction. Okay? Simple math. Let's see. And we're kind of far away, aren't we? I might have to. Well, I got till 11:30. Let's see how far we can get. Now, the equation that governs the vapor pressure here in the solution is Rayleigh law. So the vapor pressure of the solution is equal to the vapor pressure of the solvent times the mole fraction of the solvent. So if we calculate the mole fraction of the solute, then we just have to say 1 minus that mole fraction, and that gives us this value. Now this Rayleigh's law works as long as the solute is non-volatile. It's not a T, that's an L. Rayleigh's law. And this is for non-volatile solutes. We have to complicate it some if both of them are volatile. But I think for this course, we're not going to go that route. Okay, and there's an attempt to explain what's happening. You've got the yellow balls are the solute, and it's taking up space, and it's attracting solvent molecules. So they can't get into the headspace, decreases the pressure. All right. So that's one colligative property. And it doesn't matter what the solvent is. It doesn't matter what the solute is. It matters what the solvent is because that gives you this value right here. But the mole fraction, Reynolds law doesn't care what the solute is. As long as it's non-volatile, it works for any of them. Okay? Another colligative property, boiling point elevation. Boiling point elevation. So if we dissolve solute in a solvent and it gives us a concentration, then we can equate that to a difference in temperature for the boiling point. So the pure solvent is going to boil at some temperature. Say water is going to boil at 100 degrees. Or we determine it experimentally. And then when we add a certain amount of solute, the boiling point increases. And the change in temperature is equal to this formula. The change in temperature for the before and after adding solute is equal to this constant, which is characteristic of the solvent. It's called the boiling point elevation constant. And this concentration of the solute. Now the little m, we didn't talk about this one yet. The little m is not molarity, it's molality. It's similar to molarity with one major difference. It does have the moles of the solute in the numerator, but in the denominator it's kilograms of solvent. Now, can anybody imagine why we would want to use mass here instead of volume? Because the temperature's changing. You change the temperature, you're going to mess with volume. So we use a different unit of measure here. Molality instead of molarity is ratio to the kilograms of the solvent, which is mass, and it's not affected by the temperature. Okay, that's boiling point elevation. Now, when standard temperature and pressure are indicated for these types of problems, remember standard temperature and pressure for gas problems is 0 degrees Celsius and 1 atmosphere. But for all other problems, standard temperature and pressure is 25 degrees Celsius and 1 atmosphere. And then if a standard concentration is mentioned, that's 1 molar. Okay, freezing point depression. That's the one we're going to use 2 weeks from now. Freezing point depression. By the way, this change in temperature, if boiling point elevation is going to be one sign, freezing point depression is going to be the opposite sign, because instead of going up, it's going down. So what we're actually interested in is only the absolute value. The change is all we're interested in. So here, the change in, and this is boiling point change. This is freezing point change. The absolute there is similar to this one. It's a different K, right, for freezing point, times the molality of the solute. So on that previous page, boiling point elevation for aqueous solution, excuse me, I have to go back, is 0.51 would go in here for water. And for freezing point for water, it's a different K, 1.86. And this is in degrees Celsius per molality. So if we add a non-volatile solute to a solvent, how does it affect the vapor pressure? Causes it to go down. All right. So these are three colligative properties we talked about so far. The last one is osmosis. And I think we're going to do some osmotic stuff too. Yep. The one after freezing point depression is osmosis and dialysis. But they're going to be quantitative in some respects, but we're not going to do the same type of calculation with the osmosis as we do with freezing point depression. Okay, let me make some room over here for the last one, osmosis. Everybody know what osmosis is? If you've had a general biology course or anatomy and physiology, you know what osmosis is. Right. We need to define some terms, though. Osmosis. Osmosis is the process upon which osmosis is based is movement of a solvent through a membrane of some kind. Right? If the concentration of the solution on one side of the membrane is the same as on the other side, there's no movement. Well, there's no macroscopic movement. Right? Microscopically, yeah, there's activity, but you don't see any change. However, if the concentration on one side of the membrane is greater than it is on the other side of the membrane, then you're going to induce a movement of solvent through the membrane to the more concentrated side. Now, there's a difference between semi-permeable and selectively permeable membranes. When we say semi-permeable, we're saying that the only thing that can pass through that membrane, it can pass water and gases. That's it. Nothing else goes through that membrane. Selectively permeable membranes will pass small molecules. And selectively permeable membranes actually can be engineered to pass a certain size or less molecule. They can also be modified to pass only certain types of molecules, like charged versus or uncharged versus charged, and it hold all the charged molecules back and let the uncharged go through. So it's a wide range of selectivity. The one we're going to use in our osmosis lab is selective only for size. So small molecules go through, large molecules are retained. All right. So the process of osmosis, let's see. What's it look like? Here we go. So the idea here is that you have a more concentrated solution inside the tube, and the membrane is capped on the bottom of the tube. So we start off at the same level, and then which way are the molecules going to move? If it's semi-permeable through that membrane, and we have water on both sides, right? But let's just, for argument's sake, say this is pure water on that side. And on this side, we have some other molecules dissolved in it. Which way is the water going to move? It's going to move from high to low concentration. high water concentration here to low water concentration here because it has those extra molecules. So water's going to go this direction. And that's what it does there. It moves into the tube because the tube is more concentrated in its solution. The water moves in and it builds up pressure, which pushes the volume up. And it goes up to a certain point to where now the movement of water into and out of across that membrane are now in equilibrium. And the reason they're in equilibrium is because there's pressure on the inside pushing those water molecules back. So once that's balanced, then we can measure an osmotic pressure by the height of that column. Okay? So the osmotic pressure is due to the concentration in the concentrated solution in the tube. So we say it contributes an osmotic pressure. That's one way to visualize it. On the molecular scale, what you see is competition. Right? The large molecules are trying to get through the membrane and they can't. The water molecules can go through the membrane, but on the concentrated side, they're impeded by the presence of those non-movable molecules. Right? So they don't move through as fast. Some of them make it through, but more of them make it through from the concentrated, the water side into the concentrated solution. The rate increases there until you get a balance. Now, if we artificially increase the pressure on the concentrated solution, we can force water molecules back through that membrane against the gradient. Right? They want to come in from the high water to the low water or into the concentrated side of the solute. But if we increase the pressure, now we're driving the force that's driving them is greater on the inside than it is on the outside. So what we're doing is we're driving water through that membrane into that space and concentrating the solute in the tube. That's called reverse osmosis. And that's used on an industrial scale for places that have lots of energy, cheap energy, but not enough water. Like the Arab countries that have lots of oil, cheap oil, energy, they can produce lots of pressure cheaply, and they take seawater and reverse osmosis, they make fresh water out of it. But it takes cheap energy to do it because this is not an efficient process. Okay, this is a problem that has interested me for quite some time, since I was a kid. Once I learned about the sequoias in California, these huge trees, and I also learned that we needed to move water from the roots to the tops so the leaves could do their thing. Now I said, how does that water get up there? I mean, that's a long way for water to go. Well, as the years progressed, I learned about the structure of a tree, you know, where the water goes, right? It moves up through the xylem. And one of the proposed mechanisms for moving water up to the top of a 250 or 300 foot sequoia was pulling it, right? Because water has some cohesion. It moves up into the leaves, in this case the needles, and they have little pores on them, stomates. Right? You know about stomates? If you've had biology, you know about stomates. Well, the evaporation of water from the stomates and the exchange of gases into the leaf occurs through those openings, and they're controlled by guard cells. So the guard cells would swell up and close, and that would hold everything in and wouldn't let water evaporate. But when they open up, water evaporated. And then the water has surface tension. So as the water evaporated, right, these are like the walls of the cell. The water would do like that, and it would be pulling, and it would pull itself back up flat again. And that force, I thought possibly was enough, if you have enough of them, you know, lots and lots and lots, millions and billions of cells pulling, could pull the water up 300 feet. Well, some enterprising scientists, probably they're graduate students, worked on this problem, and they found that it won't work. There's not enough force available to pull that water up. So we had to go another route. So some other enterprising students or scientists measured the osmotic pressure at the roots of these trees, the difference in concentration of the solute on the outside of the root and the inside of the root. And they found that osmotic pressure inside the root, because of its increased concentration, those dissolved substances in the sap, in the roots, could supply an osmotic pressure in the root of 20 atmospheres. There's that much push to drive water up the xylem. Now my question was, if it's 20 atmospheres of push, is that enough to get water all the way to the top of the tree? So here's the solution. First, we had to find out how tall the tree is, and in terms of millimeters. Why did I choose millimeters? Because I'm going to convert 20 atmospheres into millimeters of mercury. So the pressures will be the same units of measure. Only this is just the height in millimeters. So that's how tall that tree is in millimeters, 10 to the 4th millimeters. Then, how about 20 atmospheres? What does that represent as a column of water in terms of millimeters? Right? 20 atmospheres times 760 millimeters of mercury is the height of the millimeters of mercury column. But water is less dense, so the column is going to be longer. And the ratio is 13.56. That's the density of the ratio of the density of mercury to water. So 13.56 times what I got from 20 times 760 is 2 times 10 to the 5th millimeters of water is the column that could be supported with 20 atmospheres pressure from the roots. But we only need 9 times 10 to the 4th. So, yeah, it can make it. It's about twice as high as you need. That much pressure will drive water to the top of a 600-foot tree, if we had one. So there's your answer. That's how water gets from the roots to the top of a sequoia, using osmotic pressure. Now, I'm going to have to refill my drink. I'm about out of time anyway. Let's see. I probably got 10 more slides. I guess we could... I don't want to eat up your lab time. So I'm thinking marking where we reach. 8. Here we go. You know what? We might be able to finish it. Yeah, I think we will, because those last slides don't take a lot of argument. Osmolarity. If osmolarity is a unit of measure that's based upon the molarity of the solution, of the solute, times a correction factor. And what that means is, if we have a molar solution, say 1 molar sodium chloride, but in solution it breaks up into ions, right? So what's the concentration of the ions? The concentration of the ions would be 1 molar of sodium and 1 molar of chloride. So the total is 2 molar. So the I value for this one is equal to 2 because it's 2 times over here versus 1 there. So that's what that I is. Osmolarity is this factor, this I factor, times the molarity. And all you have to do is know how the compound breaks up when it goes into solution. If we have calcium chloride, that's 2 plus 1 is 3. So I equals 3. Okay? What's the osmolarity of 3 molar sodium chloride? Well, it's 2 times. 6 osmol. Okay? Now, again, if you've had biology or anatomy and physiology, you understand tonicity, right? Isotonic solutions versus hypotonic versus hypertonic. Think of them in terms of blood cells. That 0.9% sodium chloride solution that we talked about several slides ago is an isotonic solution. For your body fluids, right? Isotonic means that for instance, your blood cells or any of the cells in your body in contact with that solution will not transfer water across the membrane, either direction. Right? They're stable. Hypertonic solution, which would be greater than this, would cause water to move out of the cell because the water concentration inside the cell is higher than it is outside the cell. Right? So this would cause, for your cells, particularly blood cells, a process called crenation. They get wrinkly because water's moving out and they're shriveling. If the concentration is lower, this is hypotonic. Hypotonic solution has higher water concentration outside the cell than inside. So, which way is the water moving? It's going into the cell. Let's see. Into the cell. Hypertonic moves out of the cell. Isotonic, no water movement at all. So there's your crenation. And for blood cells, this process is called hemolysis. Right? Heme meaning blood, and lysis meaning cut or break or split. Right? Generally speaking, we could say cytolysis. For any of your cells, they would rupture. Cyto means cell. Cell rupturing. Now, 0.9% sodium chloride is isotonic, but it's not good for your physiology. It gives you way too much sodium and chlorine in your system. But in a pinch, you can use it. Right? If you're Mark Wahlberg and you got shot, you know, then you can mix up a solution and take a radiator hose off a truck and stick it in your arm and replace some of your fluids. Right? And they're isotonic. That's a stopgap measure. What's better is, and this is for anybody but diabetics, is used a solution called D5W. All paramedics know D5W. It's dextrose 5% by weight. And that 5% mass to volume glucose is roughly equivalent to 0.9% sodium chloride in its tonicity. It's isotonic with your cells. That's why if you're diabetic, you probably need to wear a bracelet of some kind, because if they don't know that you're diabetic and they give you that solution on the way to the hospital, you might be dead by the time you get there, right, from sugar shock. Okay. Let's see. These are some details. I got the link down here. Right, you can get that link from, if you pull up the slides in Brightspace, get that link and it'll describe the problems with 0.9% sodium chloride in terms of your physiological effect. Right? You're getting more sodium than you would need, but you're getting a huge slug of chloride. And both of those together are going to mess with your kidneys, because your kidneys are going to work overtime trying to get rid of that stuff. Okay, isotonic solution where the osmotic pressure is the same on both sides of the cell walls, on both sides of the membrane. So how's the osmolarity determined? Well, the molarity of the compound times that I factor. How many units dissociate from each molecular or formula unit? All right, I'm going to skip these just so we can get it done and move on to the lab. What do you think? I'll move slow enough so the solution shows up there and there and there. It gives us the answer. Just I didn't discuss it. And then the second one, right, there's the answer for the second one. All right, and we're done.